O Solon, Solon, you Hellenes are never anything but children, and there is not an old man among you. Solon in return asked him what he meant. I mean to say, he replied, that in mind you are all young. There is no old opinion handed down among you by ancient tradition, nor any science which is hoary with age. Salut tout le monde. Today's differential geometry stream is going to be a review of the theory of curves chapter, which I just finished pretty much all of the main content for in the last stream from Differential Geometry by Erwin Kreisig. It's a Dover edition book. That's the main book that I'm reading in this series. But while these videos so far have mostly been about reading the subject of differential geometry specifically, if you've watched some of my past episodes in this series, then you might already appreciate that there's a rich history of figures who've contributed to the discovery or invention of the concepts in the subject of differential geometry. Discovery or invention, depending how you look at it, because it's math, of course. But at the same time, hopefully you can realize that the linear progressive buildup that this textbook unpacks the subject matter in is somewhat superficial in light of the history of the development of the subject, because so many sorts of different endeavors have led people to be interested in the particular problems that lead to the emergence of whatever concept it may be. That we now think of all these concepts as modern and we have them in these cleanly polished boxes, but I think the history is important and it's worthwhile to go over. But a few streams ago, I started off by playing a clip of Eric Weinstein saying,
look, if you don't know what a Riemannian manifold is, if you don't know what a determinant line bundle is, there's no way you can ask intelligent questions about alien visitation.
Now, I would take a step back and I would say that if any of a multitude of theories of the nature of non-human intelligence are true, then independent of what phenomenology are associated with the nature of the other non-human intelligences are, whatever they may be, I would contend that there are three domains that us humans as intelligences or minds or operations of consciousness, as it were, three domains that we would have in common with those non-human intelligences. And those three domains are philosophy, math, and physics. So in today's video, there's a lot that I want to get into, but I'm just going to start off with a quick overview of my reading of Western philosophy and its history, because I'm going to keep on bringing up and referencing things about philosophy specifically that you're most likely not going to see in a math class, but I think it would really help to go over it. So I also said in a previous video in this series that reading about things like differential geometry is an activity akin to taking a trip to a fancy, expensive art collection. And so with that being said, I'm going to start today looking at the School of Athens by Raphael. Now, many of you will undoubtedly be familiar with this work already. It was completed in 1511, of course, and it's a fresco in the Vatican. And Raphael's accurate use of perspective projection here is iconic in Renaissance art. But I want to discuss the word Renaissance a bit because I think it's going to be important for what I'm about to say. Renaissance is, of course, re-naître. The naître again, where naître being the French verb infinitive of to birth. So for an example, in English, we say things like, I was born on a particular date, and then in French you would say, je suis né le whenever. But what was being born again in the Renaissance? Well, part of it was during the Renaissance, as it were, ancient Greek philosophy again was coming into vogue out of the preceding Middle Ages in Europe. So for this scene here of the School of Athens, we have a milieu of ancient Greek philosophers, mathematicians, and scientists, basically, with the two undisputed main subjects at the center, the focus of this perspective projection image. We have Plato and Aristotle. And I will point out of the group of others to the left here in the green outfit, we also have Socrates. So of course the lineage goes that Socrates was the teacher of Plato, whose school then Aristotle emerged from. So Socrates, Plato, and Aristotle are like a powerhouse of Western philosophical thought, to say the least. Now, I'd like to note here that it is uncertain today how much ancient Greek philosophy that the 26 to 29-year-old Raphael during the 1500s had read or was familiar with, whether he had guidance from someone else, or even whether a detailed program for the scene was dictated by his sponsor, Pope Julius II. But nevertheless, there is a lot of loaded imagery going on, especially with Plato and Aristotle, and I'll get into that in just a sec here. But Socrates is remembered by things like his namesake Socratic method and the Socratic circle, of course, and central to each being their interrogative approach to the pursuit of capital T truth. And as a matter of fact, of course, Socrates was like Jay-Z in that he never wrote anything down, and that was intentional. So all we know about Socrates is from the writings of Xenophon and also mostly from Plato. So namely, these back and forth inquiries into understanding by Socrates, as written down by Plato, are known as the Socratic dialogues. Plato had his own original remarks in his overall Platonic dialogues, but the Socratic dialogues are a subset of Plato's works, technically. So Plato wasn't necessarily present in some of the conversations or exchanges recounted in the Socratic dialogues. Rather, Socrates, as his instructor, told them to Plato, who then wrote them down. And moving right along here, we have a work called The Death of Socrates, which is by Jacques-Louis David, or David, in 1787, where we see Socrates making his gesture upward in the plane of the painting, which is the same gesture that's being made by Plato in the School of Athens. Now, Socrates famously said, "Give me liberty or give me death," and was given death. Another famous quote from Socrates is, "I know that I know nothing," and this is reminiscent of Thales's earlier maxim, which is carved into the temple at Delphi, "Know thyself." Indeed, Socrates' ideal could be said to be knowing the self and the life of self-examination. And following this, however, Plato is critical to Western philosophy. Socrates could be seen as the grandfather of Western philosophy, and Plato is then the father of Western philosophy. In retrospect, when one describes lineages of key moments in Western philosophy, or if I'm referring to like the trajectory of Western philosophy, I'm really alluding to key moments where instead of resisting contemporary thought, the thinkers of these key moments along the way inverted and incorporated the contemporary thought into philosophical progress. And for example, after Plato, there was Descartes, who I brought up several episodes ago, and he was involved in the development of tangent lines debate with Fermat, of course, who would then get ripped off by Newton. But Descartes is nonetheless regarded as the father of modern philosophy, so keyword modern, for being a landmark figure in the rise of the systematic school of philosophy known as rationalism. But later, we would have figures such as Heidegger, who would advocate that the Cartesian turn was a wrong turn ultimately in the development of metaphysics, and Heidegger advocated for a return to the pre-Socratic. And actually, this reminds me of, this is not something from Heidegger directly. This is from a philosopher who recently passed away, Daniel Dennett. I was just watching one of his last interviews, and he made a good point that sometimes in philosophy, we get too obsessed with defining terms, and it leads to things like essentialism and so on and so forth. But we need to focus more on the problems themselves, and that part of the philosophical endeavor, this is me paraphrasing a little bit, but is that it's the gathering and the sharing and the exchange then of that experience that we gather from interacting with the problems. And part of the issue is that alongside Socrates was Euclid, and Euclid, when he was essentially rigorously deriving proofs for geometrical theorems for the first time, really for the first time, that then contemporary thinkers looked at that as the gold standard that every other type of philosophical thinking would have to match the level of rigor of geometric proof, right? Which is kind of hard to ask for. And so then that's how we get bogged down in over-defining terms and stuff like that. But return to the pre-Socratic is a theme that gets reiterated over and over. Rest in peace, Daniel Dennett. Another figure later relative to Descartes and Plato especially was, of course, Nietzsche. And Nietzsche has since been read that in Nietzsche's inquiry into the ancient Greeks, including Plato, essential to the emergence of philosophy in Plato's time was the idea of nature, and that at a high level, Nietzsche invokes, yes, the same philosopher versus tyrant duality, again in a similar yet distinct way to Plato, but in further detail, Greek society in Plato's time was arguably in a period of relative decline, and this made the emergence of philosophy particularly ripe. And so therefore, one could interpret that underneath Nietzsche and Plato's defenses for the freedom of thought and the possibility of philosophy, there lies a motivation for selective breeding for the preservation of nature. And these ideas certainly are involved with, philosophical lineages of their own, but I want to focus in on another one briefly, namely one that starts with Plato apropos sophism that concerns capital T truth. So Plato was not a sophist, but the sophists in Plato's time emphasized dialogue and rhetoric in their approach to, you could call it capital T truth, that truth can be manipulated according to these kinds of subjective enunciations. Think of it like if there were a politician giving a speech, if it got everybody riled up, then that meant that everything that politician said in the speech, according to sophists, would be true. So Plato's gesture that we would now call the Platonic transcendental, or you could briefly characterize as naive transcendentalist metaphysical idealism or phenomenological positivism, Plato's philosophical gesture used the essence of sophism, namely truth, against sophists' own core tenets of dialogue and rhetoric. So, for Plato, truth exists outside appearances. It's kind of where we get this theory of forms idea that is associated with Plato that he never explicitly talked about in his dialogues. But this statement about the phenomena associated with the nature of basis of reality is a metaphysical statement, okay? So one could argue that this stance on phenomenological metaphysics taken by Plato has been modified or refuted by other thinkers in the time since. So that's to further elaborate on what I mean by a particular philosophical lineage or trajectory within Western philosophy here. So since Plato, there is George Berkeley, who is seen to the top right of Plato, and I talked about him in an earlier one of these episodes. George Berkeley, the immaterialist who asserted that only minds and mental contents exist. And next to him, we have another guy who I mentioned before, Jean-Laurent d'Alembert, who is the father of the solution of the wave equation. And d'Alembert doubted whether there exists outside of anything corresponding to what we suppose we see. And they are just the preface, really, to, or I guess they're in anticipation of later Kant. But the critical step past Plato here was made by the guy to the right of d'Alembert. The actual real big leap, if you will, was made by Hume, who was from around the same time as Berkeley and d'Alembert. But if Plato was naive metaphysical idealism or positivism, then Hume, on the other hand, was negative idealism, which was implicit within his skeptical empiricist approach. So skeptical empiricism, of course, from an ethics point of view, it puts sense and perception before then moral reasoning later. Whereas this is in contrast, of course, to who made the next big movement, which was by Immanuel Kant, to the right of David Hume, which was with critical idealism. And of course, in ethics specifically, Kant would be the reverse of Hume, where Kant prioritized reasoning all the way to the end, of course, and then ethics come after, right? That's where we get the categorical imperative and so on and so forth. So Kant had critical idealism, but being that things start to get more modern after Kant, of course, and being that Kant was German, we can continue on specifically with German Romanticism or German idealism. So after Kant, we have to the bottom right of Plato, we have a man whose picture honestly looks like a microscope image of a tardigrade. I'm not going to lie. But this guy, Fichte, who invoked a return to positive idealism in his philosophy, made this return, which is represented by the synonymous tautological relationship I equals I, which is to say that the capital A absolute is already within. And after Fichte, to his right, we have Schelling, who then took the stance of negative idealism in that the absolute, capital A absolute, cannot be known. The example that I've heard that I really like with this, it's from a show, but I don't know which one, but it's imagine that you're being chased by stone gargoyles, but whenever you're looking directly at the stone gargoyles, they're not moving. They're just frozen in whatever pose. But then when you turn away and you're running away from them, you turn back and you see that they're in a different pose and they're closer to you. That this relationship between you running away and the stone gargoyles, that embodies Schelling's perspective on the relationship with the absolute. So after Fichte, finally, we come to, after him, George Wilhelm Friedrich Hegel, who, of course, proposed speculative idealism. So that is to say, with speculative idealism, we have that the gap between the subject and the capital A absolute is transposed back into the absolute, and that itself is the truth mechanism. So Hegel, it's important to say this, Hegel is not where dialectic is thesis plus antithesis equals synthesis. That is not correct. It's also not correct to say that history is over with Hegel. But those two things are like the middle school answer versions to what is Hegel's philosophy. Totally false, okay? A salient point for me with the Hegelian dialectic is the meaning of the German word Aufhebung, which is usually translated to English as sublation, as in the sublation of nature by spirit related to the actualization of rational self-consciousness. Sublation, in this way, stands for cancellation and preservation as the motor by which dialectic functions. So sublation can also mean to lift in roughly the three following ways. So first, sublation can mean to lift as in to lift a ban or to lift a treaty so as to nullify or cancel the ban or the treaty. Second, sublation can mean to lift as in to lift spiritually, such as lifting a fallen person, meaning that they're saved, sort of thing. Or third, it can mean to lift in an abstract way, so to elevate something in an intellectual way, to elevate the mathematics that's involved, that sort of to lift. This is a screenshot from a Simpsons episode where outside Cafe Kafka there's a sign that reads, "Now with Hegel's Bagels." And this is not explained in the context of the episode, but a good interpretation I heard of this is that a bagel is constituted by the whole, H-O-L-E, whole, which is a metaphysical void of the bagel substance, of course. Yet for Hegel, this H-O-L-E, whole, is the whole, W-H-O-L-E, of the bagel. Hegel's Bagels. So with this being said, it is argued that the three key moments of Western philosophy are thus Plato, Descartes, and then Hegel. But we have modern day philosopher Slavoj Zizek who revises this selection by positing that the three key moments of Western philosophy are rather Plato, Kant, and Jacques Lacan, which the last one, Jacques Lacan, is a bit of a curveball. He's a provocative choice because he's not widely or formally recognized as a philosopher proper, as Lacan is formally a psychoanalyst. And for Zizek to emphasize Lacan in the entirety of Western philosophical thought is at least surprising. Lacan is thought of as a radical Neo-Freudian. So, of course, it's popularly said that Freud has been thoroughly discredited. However, a few important things can still be said about Freud. First, his work was the first to emphasize, in a way that was influential, the role of the subconscious and the unconscious in conscious experience. He was the first one to really point that out. Also, Freudian concepts have had a tremendous cultural impact, whether they're true or not, to how the mechanism of psychology actually functions. So for example, the id, ego, and superego are used all the time, at least as sorts of like thinking tools for thinking about human personality. Freud's endeavor in psychoanalysis could be seen as overturned by Carl Jung, who led to recasting Freud's original endeavor in materialistic terms and then just calling it psychology. So, I mean, of course, psychoanalysis and psychology are very closely related, even though a lot of people really don't take psychoanalysis nearly as seriously as psychology, which people don't really, if that's a college major at least, people really don't take seriously. Anyways, so Lacan is not a psychologist, but a former psychoanalyst, like I said, and psychoanalysis at its best cures you of your own self-knowledge, which is a sort of anti-Socratic ideal. Psychoanalysis doesn't necessarily believe that the self exists as a unified whole, but that it exists as a result of the impossibility of being a self at all, and that the self is merely a construct. Now, there is a difference between the subconscious and the unconscious. And I think of the subconscious as aspects of experience which are contents not directly available to consciousness, but nevertheless are apparent or become so. And whereas the unconscious is by definition exclusively not conscious. And a good example, which is the most overtold joke by Slavoj Zizek, which is the coffee without cream versus coffee without milk joke. So a guy goes to a cafe and the waitress comes up and asks, "What would you like to have?" And he says, "I'd like a coffee without cream, please." And she says, "Oh, we don't have any cream. Is coffee without milk okay?" And so functionally, constitutively, there's no difference between coffee without milk and coffee without cream. However, the difference between coffee without milk and coffee without cream is, for Zizek, the difference between ideologies, and in our interactions and our daily lives, they are important in a way that goes beyond the functional, it's just black coffee. So now, Lacan's thought is very abstract at times and heavily involves notions such as the value of a sign is a signifier and what is being signified. And I'll get into all of this here really quick just for the sake of having this all in here. But many would agree that Lacan's big four psychoanalytical ideas are 1. The master signifier, 2. The signifying chain, 3. The barred object, and 4. L'objet petit a. So, and these are in no particular order of importance, but the master signifier is where the signifier falls into the signified, or for example, the phrase, "America tastes like freedom." The signifying chain is a process that, for instance, desire plays out through, which has the same structure as the rhetorical device of metonymy, and this is shown in the upper right here with graph 1. So here, this is very different, obviously, than a graph of a curve in a Cartesian coordinate system that we're comfortable with at this point, right? This is a totally different kind of graph than a computer science graph. You're not going to see this involved in a graph theory textbook, but this guy, Jacques Lacan, he made a lot of graphs. Okay, what do we have going on here? Letters are graphemes or symbols corresponding to phonemes, which in linguistics are the fundamental units of speech. So likewise, Lacan likens these symbols to fundamental units of consciousness, unconsciousness, personality, whatever's going on here. So here the S represents the sign, which then in the process of desire transforms into S prime, representing the signified. But also there is here at the bottom this triangle shape at the bottom right of the graph. This represents intention and demand as need. So by its addressing desire through a shift, that is like what happens in metonymy, this symbol transforms into the barred other, represented by the S with a single bar through it. So you go from the triangle through the curve, which represents the metonymic process of desire, to then become the barred subject, represented by S with a single bar through it, which is different than a dollar sign. The dollar sign is technically, you take the letter U and the letter S on top of each other for United States. So a dollar sign technically has 2 bars through it. And this is an S with a single bar through it. So it is what it is, but to be clear, the barred subject S bar emerges when primitive need gets parsed into demand, which instantiates desire for what is undemandable, okay? This is all important because I'm going to go somewhere with it, and it's going to come full circle here in just a little bit. So furthermore, we have the fourth big idea of Lacan, which is l'objet petit a, which indicates the unattainable object of desire, which is thus different from the big other, or the capital A, because l'objet petit a is a lowercase a, so the big other is a capital A, and that big other, capital A, constitutes otherness itself. So, this is what I mean when the graph of desire depicts intention and demand metonymically being transformed into the barred other, and that this transformation is a sliding along the signifying chain of desire. This is the way that Jacques Lacan thinks, okay? So, now these big four concepts of the master signifier, the signifying chain, the barred object, l'objet petit a, these are not to be confused with Lacan's four discourses, which involve similar such transformations as those in the graph of desire, but these are shown beneath it in these graphs below: the discourse of the master, the discourse of the university, the discourse of the hysteric, the discourse of the analyst, where the master, hysteric, the analyst, and the universities are all involved in these, their objects, if you will, involved in these transformations. I won't get into these four discourses in detail right now, but I depict their graphs alongside Lacan's graph of desire, as well as in the top left of these graphs, I put it besides a conceptual depiction of chiasmus. So I do this because Lacan advocated that we read the productions of the unconscious à la lettre, or by the letter. And this is of the unconscious, not the subconscious, okay? So clearly Lacan is a fan of rhetorical devices, and so this reading the productions of the unconscious is akin to a chiasmus, or a chiasmatic process, which is the reversal of grammatical structures in successive phrases or clauses, but no repetition of words. For example, the crown is worn by the king, and the king wears the crown. So the crown here critically represents the authority, power, etc., wielded by the king as a person and as an official title symbolically. So the word chiasmus is from the Greek word for crossing, or to make like a letter chi. And when I mentioned earlier that Hegelian speculative idealism consists of the gap between the subject and the absolute being transposed back into the absolute, and that this is the truth mechanism in itself, for Lacan, where the self is a construct and therefore is always the barred subject, this gap in Hegelian speculative idealism is essentially equivalent to Lacan's barred subject, which represents the indivisible remainder. But we return back to the ancient Greeks and the school of Athens, which is keeping this philosophical rant of mine grounded. But we return to the focus of the piece, Plato and Aristotle, and we see that Aristotle, with his rhetorical gesture being his flat overturned hand coming directly into the space of the viewers, we see that Aristotle is anachronistically holding a bound book called Ethics. The anachronism is that there were no books bound like that in Aristotle's time. It wouldn't be until, of course, the 1400s that we have the Gutenberg press. But anyways, Aristotle did write a text on ethics. We know it now as Nicomachean Ethics. But I think Mortimer Adler, an expert on Aristotle, if you will, a modern expert on Aristotle, he put it best when he said, "The glory of man is his intellect. Perfection of the intellect is the highest thing he can achieve, but moral virtue is indispensable to that." So, interestingly enough, in another one of Aristotle's works called Prior Analytics, Aristotle coined what a syllogism is, which of course is a kind of logical argument that applies deductive reasoning to arrive at a conclusion based upon two propositions that are asserted or assumed to be true, with the famous example being, all men are mortal, Socrates is a man, therefore Socrates is mortal. And this is a deductive inference. So we start with a given hypothesis, that is a statement about how nature works, and predict what we should see if that hypothesis were true. Predictions are true if the hypotheses are true. But deductive inferencing is, of course, in contrast to inductive inferences, where whichever hypothesis is most tenable is evaluated on the basis of what is observed. So the example I think of for inductive inferencing is Sherlock Holmes. Sherlock Holmes walks into a room and makes a hypothesis solving the mystery based upon his keen observations. So This is a bit of a tangent, but I think we need to take this moment to remind ourselves that inferencing is distinct from null hypothesis testing, which is technically a behavior in that a decision is made whether to reject the null hypothesis or not. That the behavior is that decision regarding rejection of the null hypothesis. And furthermore, we need to keep in mind the distinction between null hypothesis testing and what a p-value is, and recognize the impact of experimental design in each of these things, and so on and so forth. So, now, coming back to philosophy, whereas Plato, alike in his rhetorical gesture, is a bit more heady and cerebral in his philosophical approach, Aristotle, so too, like his rhetorical gesture into the plane of the real viewers, is a bit more embodied in the real world, perhaps to a fault. So some would say that Aristotle is the father of Western civilization, not just one of the originators of Western philosophy, but the father of Western civilization, particularly due to his linguistic usage of the word barbarian. So supposedly, Aristotle thought that blind people were inherently smarter than deaf people because at least blind people could learn to speak Greek and therefore at the time be educated, whereas people who can't hear can't learn. So furthermore, Aristotle considered anyone who couldn't speak Greek a barbarian. So deaf people in Aristotle's time can't speak Greek. If Aristotle thinks that people who can't speak Greek are barbarians, therefore deaf people are barbarians, according to Aristotle. Some more background on Aristotle's theory of cognition can be found in his writing that only humans are rational in contrast to animals. And later, Descartes would double down on this, and he would say that only humans are agentive decision makers, whereas animals are merely reflexive automata. However, this has all been said when, as a matter of fact, there are no non-human primate species in Europe. There were none in Socrates, Plato, and Aristotle's time, and there still are none today. And this, of course, is having said nothing about evolution either. So, therefore, according to Aristotle, rational Greeks, distinct from everyone and everything else who's a barbarian, is the start of Western civilization as we know it, and that over time, the considerations involved with this term have become gradually more widely encompassing beyond Aristotle's initial ancient rational Greek humans, of course, but that's another conversation. So now, whereas Aristotle is holding a book titled Ethics, Plato, making his teacher's famous gesture into the air in the school of Athens, is holding a book titled Timaeus. And I'm fascinated with Timaeus. Timaeus was supposedly the only work of Plato's which was translated to Latin during the Middle Ages preceding the time period when the School of Athens was painted, and thus would have been the only one of Plato's dialogues to be available to the literati of Europe at that time. Also, if you've ever heard of Platonic solids, of course, the tetrahedron, cube, dodecahedron, octahedron, and icosahedron, or basically the family of 3D volumes that twisty Rubik's Cube type puzzles are shaped like, the credit or origin of these so-called Platonic solids is from this particular Platonic dialogue, Timaeus. So Timaeus is classified as one of the Socratic dialogues within the overall Platonic dialogues, but Socrates actually doesn't say much in Timaeus, as much as Socrates says things like, "The prelude is charming and is already accepted by us. May we beg of you to proceed to the strain." And then Timaeus goes on an uninterrupted 50-page rant about the formation of the universe and an explanation for its apparent impressive order and beauty. The character Timaeus is a mature adult with a background in astronomy and supposedly of the Pythagorean school of thought. And this 50-page rant constitutes basically a summary of his intellectual achievement. So take it for what you will. So, a fun fact is that Platonic solids could more accurately be referred to as Timaeus solids, or Pythagorean solids, even if you really think about it. But let me back up a little bit. The setting of Timaeus, the Platonic dialogue, is that three guys, Critias, Timaeus, and Hermocrates, visited Socrates, and Socrates gave a speech with content basically like what's in the Book of the Republic by Plato. Afterwards, it's the guests' turns to make intellectually stimulating philosophical speeches, of course, obviously. So after a quick prologue by Critias, Timaeus gives us his long-winded, uninterrupted speech. Timaeus says things like, when the eternal God was manipulating the essence of nature, first of all, he took away one part of the whole, and then he separated a second part, which was double the first, and then he took away a third part, which was half as much again as the second, and 3 times as much as the first. And then he took a fourth part, which was twice as much as the second, and a fifth part, which was 3 times the third, and a sixth part, which was 8 times the first, and a seventh part, which was 27 times the first. After this, he filled up the double intervals, that is between 1, 2, 4, 8, and the triple, that is between 1, 3, 9, 27. Cutting off yet other portions from the mixture and placing them in intervals so that in each interval there were 2 kinds of means, the one exceeding and exceeded by equal parts of its extremes, as for example 1, 4/3, 2, in which the mean 4/3 is 1/3 of 1 more than 1, and 1/3 of 2 less than 2. The other being that kind of mean which exceeds and is exceeded by an equal number. For example, over 1, 4/3, 3/2, over 2, 8/3, 3, over 4, 16/3, 6, over 8, and over 1, 3/2, 2, over 3, 9/2, 6, over 9, 27/2, 18, over 27. Where there were intervals of 3/2 and of 4/3 and of 9/8 made by the connecting terms in the former intervals, he filled up all the intervals of 4/3 with the interval of 9/8, leaving a fraction over, and an interval which this fraction expressed was in the ratio of 256 to 243. For example, 243 to 256, 81 to 64, 4/3, 243 to 128, 2, 81 to 32, or 8/3, or 243 to 64, or 4, 81 to 16, or 16 to 3, or 242 to 32, or 8. And thus the whole mixture out of which he cut these portions was all exhausted by him. This entire compound he divided lengthways into 2 parts, which he joined to one another at the center like the letter X, and bent them into a circular form, connecting them with themselves and each other at the point opposite to their original meeting point, and comprehending them in a uniform revolution upon the same axis. He made the one the outer and the other the inner circle. Now the motion of the outer circle he called the motion of the same, and the motion of the inner circle the motion of the other or diverse. The motion of the same he carried round by the side, that is to say, of the rectangular figure supposed to be inscribed in the circle of the same, to the right, and the motion of the diverse diagonally, that is, across the rectangular figure from corner to corner, to the left. He gave dominion to the motion of the same, and like. For that he left single and undivided, but the inner motion he divided in 6 places, and made 7 unequal circles, having their intervals in ratios of 2 and 3, 3 of each, and bade the orbits proceed in a direction opposite to one another. And 3, Sun, Mercury, Venus, he made to move with equal swiftness. And the remaining 4, Moon, Saturn, Mars, Jupiter, to move with unequal swiftness to the 3 and to one another, but in due proportion. But what has really stood out to me from the Timaeus dialogue lately is a line from Critias's prologue. You see, in this prologue, Critias tells a story he heard when he was a young boy from an old man named Amminander about a guy named Solon who was a kinsman of Critias's great-grandfather. So to keep the perspective here, Solon is a kinsman of Critias's great-grandfather, and Critias now, as a mature adult, is telling this story to Socrates, who told the story to Plato, who wrote this all down, okay? So in this story, Solon went to Egypt during what we would now say is the end of the third intermediate period, which happened around 653 BC, which is also equivalently the beginning of what we would now call the late period in ancient Egypt. So end of the third intermediate period, beginning of the late period is about the time when Solon, this Greek guy, would have been traveling to Europe or to Egypt. For context, the Great Pyramids are widely accepted in the mainstream to have been constructed in the centuries around 2500 BC. So I've already briefly mentioned Thales earlier with Know Thyself, who alongside Solon together were two of the 7 original founders of ancient Greece. And Thales is known to have been influenced by geometry that he was exposed to in Egypt around the time of this story about Solon in Egypt in Timaeus that Critias is telling. So Solon went to Egypt, specifically to the city of modern-day Sais. I'm probably not pronouncing that correctly. Sorry, Egyptians. To this city came Solon, and was received there with great honor. He asked the priests who were most skillful in such matters about antiquity, and made the discovery that neither he nor any other Hellene knew anything worth mentioning about the times of old. On one occasion, wishing to draw them on to speak of antiquity, he began to tell about the most ancient things in our part of the world, about Pharoneus, who is called the first man, and about Niobe, and after the deluge, of the survival of Deucalion and Pyrrha. And he traced the genealogy of their descendants, and reckoning up the dates, tried to compute how many years ago the events of which he was speaking happened. Thereupon, one of the priests, who was of a very great age, said, "O Solon, Solon, you Hellenes are never anything but children, and there is not an old man among you." Solon in return asked him what he meant. "I mean to say," he replied, "that in mind you are all young. There is no old opinion handed down among you by ancient tradition, nor any science which is hoary with age." Okay, and this concludes my philosophical rant for now, and really quickly I'm going to read arguably a differential geometry reference I recently came upon in Gravity's Rainbow to help transition this video a bit closer towards differential geometry again. And this is starting at the bottom of page 402 of the Penguin edition. This is what the cover looks like. Mine fell off. All Margarita's chains and fetters are chiming. Black skirt furled back to her waist, stockings pulled up tight in classic cusps by the suspenders of the boned black rig she's wearing underneath. How the penises of Western men have leapt for a century to the sight of this singular point at the top of a lady's stocking, this transition from silk to bare skin and suspender. It's easy for non-fetishists to sneer about Pavlovian conditioning and let it go at that, but any underwear enthusiast worth his unwholesome giggle can tell you there is much more here. There is a cosmology of nodes and cusps and points of osculation, mathematical kisses, singularities. And that is just par for the course for Thomas Pynchon, I would say. This is an incredible book, Gravity's Rainbow. Okay, I am going to read a viewer comment that I really liked on one of my previous videos. This is the first time someone is getting a repeat Differential Geometry Stream Audience Award. This is a comment from Vanderhagen the Stampede. Thank you once again, Vanderhagen the Stampede, for all of your insightful comments. This individual definitely knows their stuff when it comes to the math, the physics, and the philosophy. And so I'm going to read this comment here, which is on my last video, Curves in Minkowski Space. Go check that video out if you haven't watched already. We have, if a light cone is a geometric representation of the causal structure of space-time, we can think of a word line as a representation of the path of objects or particles through space-time. of course, in the context of special relativity. In this context, just as vectors in Minkowski space are characterized as space-like, time-like, or light-like, word lines can also be classified based on their properties. The Frenet equations help classify world lines based on their curvature and torsion, providing information about the nature of the trajectories and the type of motion experienced by objects through spacetime. I think the first usage, which is word line, should actually be world line. There's a missing L because I believe that the correct term described is world line. But yes, thank you, Vanderhagen the Stampede. Excellent comments. Merci beaucoup. This is a good segue, having a little bit of the touch on the physics, because I'm going to skim a little bit from these two books, which are on screen now. We have to the left, General Relativity, Wald's book. And on the right, we have this Dover theoretical physics book. I'm going to start off with the theoretical physics book because I originally, when I was an undergrad, I'm going to tell you guys a story of my own here. I wanted to double major as an undergrad in math and physics, but due to financial reasons, being that I'm poor, I could not double major, and so I had to choose just one major, and I decided to go with math, obviously. And why did I make that decision? Well, I think a good example is here in this book, Theoretical Physics. In this chapter here, we're going for derivations of equations for the force on a charged particle due to an electric field, electrostatic field. And so the theoretical derivation involves the thought experiment of having metal plates and there's an oil droplet between the plates and the plates are charged. So you don't have to read everything on this page, but from a math perspective, I like the equations, of course, right? So we start off here with equation 2. We have d phi equals field E ds. Okay, that's fine, where S is a finite surface and we're trying to get flux. So hence the flux through any finite surface S is the integral on S of E ds equals flux. Okay, fair enough. But within a lot of undergrad physics, there are these certain moves that I just really didn't appreciate at the time. So if we keep going down here, it says, if in the experimental arrangement that we're using here, we take the surface S so that it does not intersect the plates, we find that the integral vanishes. That is, no lines of force originate in the space between the plates. And it just kind of, I understand where it comes from in a physical, material, intuitive sense. However, I feel like when I was in school, I wanted to learn something or like get exposure to certain kinds of skills. And that's why like mathematical training, if you will, was like more appealing to me because, I mean, obviously this is what would be called physics type thinking, that like really gifted physicists are able to sit down and they'll not only be able to look at the equations and, you know, they can read Kuhnel's math book, they can read the Kreisig differential geometry book, so they can get over that level of, you know, must be this tall in order to ride the physics train. You need to be at least this math tall. They can get over the differential geometry hurdle that way. But then they run into things and they get themselves unstuck with their physical intuition. Okay, I get that. But I was like, you cannot teach someone that physical intuition. So I was like, I didn't really want to keep hanging around in physics classes. But looking back on it, you have more opportunities in a physics program to get exposed to like lab experience or just the enculturation of like grad students, professors, whatever. That's like the really critical part of networking and stuff. I would just I was like, dude, I just want to go and sit, and if I can read the math books and I don't have to go to class because they're not taking attendance, just do homeworks and exams. That was more aligned with my thinking at the time. But yeah, we go from the infinitesimal of flux equals EDS, we take the integral, and then the next line is we think of a different experimental arrangement so that the integral vanishes. That was always a little bit bogus to me, is the moral of that story. So now I'm going to skim a little bit from Wald's general relativity, because let's say that in another parallel universe close by, I got an undergrad degree in physics instead. And then I miraculously, or whatever adjective you want to throw on there, made it to physics grad school. And I'm like, oh, you know what? I'll just self-study math on my own, but now I'm going to go take a high-energy physics class or general relativity class. They slap this book on you day one, and they're like, we're going to be reading from chapter 9, 10, and 11 for the first couple weeks of the class, and you're just like, whoa, I'm totally caught off guard by that. I feel like that is a common occurrence in physics, and I'm going to tell you why. So we're just imagining that we're scrolling through this book. Sorry about the lines on the display. We're in, okay, like there was a notation page here. Yeah, like set theory notation. Yeah, no big deal. Like I got this. And you're like reading this. You're like, okay, yeah, I got this, bro. Okay, fundamentals. Okay. So far, yeah, it's talking, Einstein, special relativity. Oh, here we go. We got that double cone, right? We got Minkowski spaces. We're like, psh, this is totally nothing. I got this. Oh, t prime equals t, x prime equals x minus vt. Pff, nah, dude. Mathematicians are so full of themselves. And you keep going. You're like, oh, dude, chapter 1, that was nothing. Okay, chapter 2, manifolds and tensor fields. All right, this is still good. Okay. Magnitude of x minus y equals, oh, we got this sum, and we have all these, exponents on exponents. That's still nothing. But then now it's starting to like kick up a notch, and it's like, uh-oh, the set theory is getting more involved, and you're like, ooh, we've got n-dimensional manifolds here. Starting to look kind of dicey with, basis, like things are tangent field. Things are getting more intense, right? We've got tensors, finite dimensional. We've got all these cross products on top of each other. When you've got a time symbol or a plus symbol that's got a circle around it, you're starting to get into a little bit of trouble here, okay? So things are definitely starting to get a little bit dicey. So you're like, how bad could the problems be, right? How bad could it be? Problem 1, show that the overlap functions f superscript plus or minus subscript I composed with the inverse except on a different subscript index j are in infinite dimensional complex, I'm assuming, thus completing the demonstration given in section 2.1 that S2 is a manifold, right? Like that, I would say, is like par for the course, pure Mathville differential geometry. But if you just slap that on someone who's used to previously in undergrad, they read their theoretical physics book and they're like, oh yeah, d phi equals EDS, you take the integral, oops, do a little bit of magic, and now you can just, the integral vanishes, and then you pop them into this, right? Like for probably the average person who's watching one of these streams, hopefully by now you're not surprised by that level of math. But I imagine how that could be hard for a physicist. And if you don't, as a physicist, go hard on your own in the math department and like really teach yourself that stuff, but you just try to like do what you need to get by in your graduate level general relativity class, then when you're actually like trying to like come up with your own new research or whatever and stuff, it's all couched in the language of differential geometry and doing math at a certain caliber, right? This isn't just like, you know, crayon picture of the stick figure guy with the sun in the corner anymore. It's like you have to know a little bit about like how to use the paint and stuff now. You know what I'm saying? You need to get your hands dirty with this stuff, my man. So, I don't know, I just wanted to skim the physics books before we get into the differential geometry. And in the spirit of, oh, yeah, we're going to cut this into another one. Okay, so I'm going to compare roughly the contents of the Kreisig book and the Kuhnel book now. But instead of looking at each text side by side here, I actually did a little bit of preparation here and I typed up some notes which outlines the Kuhnel book here. And I don't know, if someone asks in the comments, then I'll edit the description and I'll make some way that you guys can download these notes here, but I'm just going to skim through them. It's about a dozen pages to cover, I don't know, maybe like 30 pages in the Kuhnel book, 50 pages, I'm not sure, for the chapter in the Kuhnel book, which corresponds to the theory of curves chapter in the Kreisig book, both of which coincidentally just happen to be chapter 2. But the notes here we have for the Kuhnel book, it starts off with a prerequisites chapter, just like the Kreisig book, although I will say the Kuhnel book is a little more rigorous because we have things like the inner product brought up in the prerequisites chapter for the Kuhnel book. We also have a whole subsection on Rn as a topological space. And a good way to size up the Kreisig book, the Kuhnel book, and then the MIT OpenCourseWare lecture notes is how intense of a definition of the derivative do they give. So they just, in the Kreisig book, it was just the simple, you know, epsilon delta single variable f of x, and then, you know, if you have a vector parametric representation of a curve, each entry, it was just a single variable t, right? So there, that was the extent of the derivative in the prerequisites for the Kreisig book. This one, however, it goes with a Jacobian, okay? So it's a little more intense in that regard, whatever intense means to you. Then we have more definitions, though, which are not present in the Kreisig book. We have k-dimensional submanifold. We have tangent bundle in the tangent bundle of Rn. So there you go, Eric Weinstein. And then we have the tangent space to a submanifold, normal space along a submanifold. Oh, and there goes the battery. And then we come to chapter 2, curves in Rn. Starts off with a definition, a regular parametrized curve, while in the Kreisig book, that's called an allowable parametric representation. Keeps going, we have a lemma, and then we have some examples. Line, circle, that's nothing, but then we get to our beloved circular helix that at this point we're pretty familiar with. Then we have an example of a nil parabola or a semi-cubical parabola, and that actually was from section 18 involving the canonical representation in the Kreisig book, where the semi-cubical parabola is in the normal plane, and there are two other projections in the tangent and rectifying planes, if I'm not mistaken. Example 5, catenary, that is problem 9.2 in the Kreisig book, and then the tractrix was not in chapter 2, but it is actually in section 93 of the Kreisig book, which is part of a chapter which is just a bunch of examples of different kinds of curves. So, and then we have a remark about the Taylor expansion of a curve, and that is gone over in section 18. Again, canonical representation of the Kreisig book. We go on to have a definition which is not for once in the Kreisig book, which is for a Frenet curve. Like I said, everything is titled with Frenet in this part of the Kuhnel book, but it's just basically that the tangent vectors are all linearly independent from each other. So not that big of a deal. Oh yeah, I can't forget this. Yeah, I can't forget this. For a Frenet curve, this last part here, note one obtains the vectors e1 through en-1 from C prime through C with n-1 primes by means of the Gram-Schmidt orthogonalization procedure. The classical Gram-Schmidt procedure is numerically unstable in that it introduces rounding errors. It's not a truncation error, but it's a round-off error. This is really important. In books like Linear Algebra Done Right, it will also bring up Gram-Schmidt, I believe, as a means of finding eigenvalues. Okay, but Gram-Schmidt gets thrown in the trash in numerical linear algebra. So when you're actually doing linear algebra on a computer, you do not do Gram-Schmidt. Instead, you do QR factorization. So basically, when you do Gram-Schmidt, you're using orthogonal vectors. For QR, you're using what's called a householder reflection. I think I even have this pulled up. Yeah, so right here, a householder reflection or householder transformation is a transformation that takes a vector and reflects it about some plane or hyperplane. I think the figure here and its caption are a little more insightful. The goal is to find a linear transformation that changes the vector x into a vector of the same length, which is collinear to E1. We could use an orthogonal projection, which is Gram-Schmidt, but this would be numerically unstable if the vectors x and E1 are close to orthogonal. Instead, the householder reflection reflects through the dotted line chosen to bisect the angle between x and E1. There you have it. So you could solve ax equals b thus using QR factorization. First, you would compute the QR factorization of a equals QR. Then you would compute y equals q star b, where q star is the conjugate of q, times the vector b, and then you would solve r times x equals y for x, which is what you originally wanted to solve ax equals b for. So you could use QR factorization to solve ax equals b, but QR is numerically superior to Gram-Schmidt. So I guess to elaborate on that a little bit more, Gram-Schmidt is numerically unstable because of the inexactness of the representation of real numbers and the operations on them. So you're limited by what your precision is that your computational machine, so-called, is capable of doing. So the more decimal places that you allow in your computation of the Gram-Schmidt process really limits you in how accurate you can be. I guess to say a little bit more about numerical stability, I don't know, there's this other part of the Wikipedia page for numerical stability where it goes over not Gram-Schmidt and, you know, computing orthogonal vectors and stuff, but it's for the algorithm for square root. And there is an interesting historical aspect of this. To tie it to all that ancient Greek stuff in the beginning, it talks about the Babylonian method for computing square roots. And, You guys can read it all if you want on your own, but going down below here, it says, by comparing the two results above, it is clear that loss of significance caused here by catastrophic cancellation from subtracting approximations to the nearby numbers, the square root of 501 and the square root of 500, despite the subtraction being computed exactly, has a huge effect on the results, even though both functions are equivalent as shown below. You can read what you want below. But this cat. Okay, so next we have plane curves with constant curvature. This is in the Kreisig book as well. This is from section 12. It is example 1. This says a regular curve in R2 has constant curvature kappa if and only if it is part of a circle of radius 1 over the magnitude of kappa, if kappa is non-zero, or a line segment if kappa is equal to 0. Excuse me, Mr. Catboy. However, the example in the Kreisig book, the circle of given radius implies constant curvature is what the example is, which is only one direction for this theorem. So then it goes on. 2.7, there are some remarks which include the Cornu spiral example, which is given in section 21 of the Kreisig book, which is merely examples of curves and their natural equations. The Kuhnel book goes on, space curves, a corollary involving the Taylor expansion of the accompanying three-frame or Frenet frame. 2c, relations between the curvature and the fundamental theorem of the local theory of curves. And then 210, theorem, osculating sphere and spherical curves. That should definitely sound familiar. That is section 19, contact osculating sphere, obviously from the Kreisig book. Theorem, slope lines. This is not in the Kreisig book. Okay, and there's this example here. Curves with constant Frenet curvature in R3. This is brought up in the Kreisig book as theorem 15.1, which is due to our boy Lancret. And that's spelled out in the book. Some remarks on the skew-symmetric Frenet matrix, and then we have a remark about the Darboux equations, which itself was theorem 16.2 in the Kreisig book. 2D, the Frenet equations and the fundamental theorem of the local theory of curves. Kind of felt to me like just doing the Frenet equations in general Rn. So then we come to 2e, curves in Minkowski space. That was the last episode. So we can skip ahead. Now there's a lot that I guess I really could have read the entire Kuhnel book, section 2f, the global theory of curves, but that was like 10 pages. So I was like, I really want to do this review so I can get on with going to the next chapter in the Kreisig book. So I guess to compromise, I'll just kind of like skim over the definitions and theorems here. Definition of a closed curve, what it means for a curve to be periodic, simply closed. I think that was in section 6 of the Kreisig book as well. Curvature in polar coordinates, theorem and definition of polar angle function and a winding number. Winding number comes up in the MIT OpenCourseWare notes that I'm going to go over here in just a little bit. Definition, rotation index, corollary, the rotation index of a closed and regular plane curve is equal to its total curvature divided by 2 pi. Lemma theorem, theorem on turning tangents. Total absolute curvature, that's also in the lecture notes. Definition of convex. Characterization of convex curves, total absolute curvature, another corollary. Four vertex theorem, total curvature of curve spaces, and a theorem due to Friedrich Fabricius Becher. Then we get to the chapter 2 exercises. Now, if I'm not mistaken, Okay, so now we're at the exercises at the end of chapter 2 of the Kuhnel book. So interestingly enough, the exercises were not interspersed through the sections in the Kuhnel book like they are in the Kreisig book. But anyways, I didn't do any of these exercises really, except notably exercise 25 is Bertrand curves, and it has show that non-planar Bertrand curves are characterized by the existence of a linear relation a kappa plus b tau equals 1 with constants a, b, where a is non-zero. That was the whole entire section of section 23, I'm pretty sure. Right? It was section 23. It was at the end of chapter 2 of the Kreisig book. But yeah, that will conclude the overview of the difference between the contents of the Kuhnel book and the Kreisig book. This is a marathon of a stream here. Oh my gosh. So now I'm gonna skim the MIT OpenCourseWare lecture notes here. So yeah, we've got a lot of stuff that we've already covered, but they jump into Frenet equations, jumping right into curvature right on day 1 after, some short preliminaries. 2, okay, still kind of just, reparametrizing things. Unit speed curve. Okay, we can handle all this stuff. Okay, and you know how I was saying you can size up the Kreisig book, the Kuhnel book, and these notes by their definition of a derivative? Here we really have stuff where we're not in, where we're looking at the Hessian matrix, so the matrix of second derivatives. So we're really ratcheting up the notation that we're using here. But still, we can handle all this stuff. Looking at the Minkowski space double cone stuff here in lecture 4. I will also say that there's 10 lectures in the OpenCourseWare in order to get through the theory of curves, and I had about 10 episodes of reading from the Kreisig book. So time-wise, it could be argued it's probably about equal. I don't know. Regular curves, Frenet curves, lecture 5, lecture 6, yeah, okay. Lecture 7, okay, this is starting to get a little bit out of hand from what was in either of the books. T periodic smooth function, and then we have the degree of f, so we're getting a little bit more stuff, but then we come back to the winding number of f around p, so that was definitely in the Kuhnel book. And we've got a closed curve, Jordan curve theorem. I don't know about that. Then we have the total curvature of a closed curve, so that was in the Kuhnel book. Okay, looks good, rotation number, whatever. Okay, this is definitely not in the Kuhnel book or the Kreisig book. Hopf-Umlauf-Satz theorem. Let C be a simple closed curve, then the total curvature of C is equal to positive negative 2 pi. Not ringing any bells, but there are definitely homework problems associated with the OpenCourseWare that definitely it's like you're digging into this with an exercise. I'm not doing it today. Definition, convex, awesome. Closed curve, theorem, Whitney, no proof. Let C be a closed curve with normal self-intersections. Got it, I guess. Then we've got lecture 10, Sturm-Hurwitz. Let F, which maps R to R, be a continuous 2 pi periodic function, so that. Then we've got these integrals. Definitely not in the Kuhnel book, definitely not in the Kreisig book. And we have a couple of lemmas. 4 vertex theorem, strictly convex version. I'm gonna read. So with the MIT OpenCourseWare for this course, or for their differential geometry course, 18.950, there are 3 homeworks that could be associated with the theory of curves content here. And there are, between these 3 homeworks, 8 problems total. 3 in homework 1, 2 in homework 2, and 3 in homework 3. And just for time's sake here, I'm going to do 1 problem from homework 1 and 1 problem from homework 2. So the problem from homework 1 I chose here is problem number 2, which is simply compute the curvature of an ellipse. Where does it reach its maxima and minima? And I'm leaving out the maxima and minima part because like this whole problem is just a real plug and chug algebraic computation problem. So you look up the equation for an ellipse if you're like me and you forgot it off the top of your head because you're just like, I don't know, whatever. So we have x of t equal to a cosine t and b sine t, where t, the parameter, is greater than or equal to 0, less than 2 pi. And critically, we use the formula for curvature involving the t derivatives of the vector parametric representation of our given curve here, the ellipse, not the equation for curvature for the vector parametric representation in terms of arc length, which would be kappa of s. So we're going to use the formula for kappa of t, which is this big, I called it atrocious the first time saw it in the earlier stream where we go over the derivation of this, but it's the square root of the entire quantity of the dot product of the first derivative of the vector x with itself times the second derivative vector dot producted with itself. So those 2 dot products results multiplied with each other minus the square of the dot product of the first derivative and the second derivative of this vector x. That is all taken a square root of over the 3/2 power of the dot product of the first derivative x with itself. So you can work this all out on a piece of paper and you get the equation for the curvature of an ellipse, which is not any less atrocious now that there's an actual function that has been evaluated using this formula. You see what I'm saying? So we have this whole quantity a squared b squared, closed quantity times another quantity, which is the 4th power of sine plus the 4th power of cosine, closed quantity, plus 2b squared a squared times sine squared of t times cosine squared of t. That's all in the numerator. I'm not going to read what's in the denominator. And I stopped there. I'm not going to do the maxima and minimum part because all you have to do is, I mean, I say that as if it's no big deal, but you just take the derivative of this curvature of an ellipse expression that we've worked out here. Take the derivative, set it equal to 0, solve that. I'm not going to do that right now. You see what I'm saying? Because that's rough there. That's rough. Homework 2, problem 2. For this problem, you'll need elementary knowledge of the complex numbers, at least knowing how to do arithmetic operations on the complex plane equal to R2. See previous stream for a rant about the complex numbers, okay? You'll also need Maple or Mathematica. Psh, F that. This MIT OpenCourseWare is from a course that they taught in 2008. I'm going to use MATLAB, thank you very much. Even though, you know, the whole vectors start at one thing, not at 0. Anyways, we're not going to go on a rant about MATLAB. On the positive side, you don't need to give proofs for your insights. Thank you very much. That's why I chose this problem. Let P be a polynomial. For instance, P of z equal to z to the 4th over 4 minus 8/3 z cubed plus 17/2 z squared minus 10z. And then we have 2 other polynomials. I'm not going to do them. Fix some radius r and take the closed 2 pi periodic curve c of t equals p of r times exponential of I times t, or e to the it. How does the total curvature vary with r? Where are the jumps and how many are there? Let the computer draw some pictures for you. And we are going to have the computer draw some pictures for us. All right. So on the xy plane here, I have plotted 5 examples of each of the complex plane representations of this polynomial for, yeah, I don't know what else to tell you. And then on the z-axis, I put the different values of r, which at the lowest value that I plotted here, I chose r equals 1 for obvious reasons. It's not very zoomed in, but we can zoom in here in a little bit. We have these, I would describe it as like a cardioid shape almost, but this looping back on itself, not exactly circular shape here. I was a little bit thrown off by this because the word jumps, where are the jumps and how many are there? I didn't know what was meant by a jump. These figures here, I don't think they actually connect at 0 and 2 pi. There's a small gap, but there isn't a jump per se. But if a jump means a crossing over point or a point where there's like a cusp, then from values of r of 1 to 10, which I calculated out here, but I only showed r from 1 to 5, and I only chose integer values of r. I didn't look at like r equals 0.5, 1.5. But the number of crossing over points for 1 was equal to 1, for 2 it was equal to 2, 3 it was equal to 3, 4 goes back down to 2, 5 goes back up to 3, and then for r equals 6 through 10, crossed over about 4 points. Crossed over on itself or formed a cusp. I didn't have enough time to look into it any further. I don't know. We could look at a zoomed in, let's see here. Oh, shoot. This is what I mean. So this is for r equals 6. And we can see that it crosses over on itself 1, 2, 3, 4 times. That's what I mean. On this little tiny bit here, it actually makes like a little loop in there. So I counted the tip of that as like 1 because I'm pretty sure if we zoom in, yeah, it doesn't connect there. But then we have one other crossing right there. So I counted that as like 2 jumps. Okay, and then it crosses over on itself 1, 2 more times. So I counted that as 4. I don't know what this question was sort of asking for here, but obviously I'm really competent at being able to use MATLAB, so it's kind of like, what else could you want from me at this point? That's all I have to say. This is going to be a huge editing challenge, so I'm going to just end it right here. Thanks if you made it this far. Peace.